know that this doesn't give me all possible Sudokus? Well, I know this because we can count all possible Sudokus, and then we'll see that there are more Sudokus than there are elements of the group. So by counting, I know that I can't possibly get everything from a smaller set in a bigger one. And the way you do this is really, it's very involved and kind of tedious. You first you relabel, so I eat up those actions, and say that the first block is in the standard counting order, 1 to 9. And then what I do is I count all the ways I can complete the first row. You can actually just enumerate all of them. And then I figure out all the possible ways I can complete the first blocks. And you get some insanely huge number. But it's actually not hard to sort of work out in reason through. And then you use the other group operations to push the first row of blocks into sort of a nice form, and then rearrange the lower ones a little so that basically you try and make it so that they are in increasing order as much as you can. And then you can count the rest of them.
Almost really.
It's big. I'll just leave it at that. All that is the contrary. I actually did try this out before, and that didn't do this. Let's figure out just how big. So these are thousands, millions, billions, trillions, quadrillions, quintillions. It's just like a 6.6 or sort of sextillion. How the number. So really, really big. Really much bigger than we saw before, and much, much bigger than the like 3 million or so that we had. So one thing this does do, and one thing the group operation lets us do, is it takes this really huge thing that we have and lets it be cut down into a smaller size. So one of the things that we get is we can ask how many inequivalent Sudokus are there. I mean, they aren't the same by the group action, and there you get a much smaller number, 5.4 billion. So that's not, I mean, it's really big from our perspective, but it's really small from a computer's perspective. So if you want to do, say, a brute force computation of enumerate all of the possible Sudokus and check properties of them, a computer can do this for something that has 5 billion things. A computer can't do it as well for something that has 6.6 sextillion things. It's going to be a lot harder. And so here's an example of what people have done with brute force computations. You can ask, what's the minimum number of filled-in squares you need to actually be able to solve a Sudoku? And the answer is 17. Yeah. How they check this? They exhaustively listed all 5.4 billion Sudokus, and then they cut out numbers until they found that, oh, you know, if I use for any of them and I have only 16 squares, I don't get a unique solution. So, and here's a grid. It has only 17 numbers, and you can fill it in. So it's one of the examples. Okay. So, over time. So I'll just quickly go through this since I'm out of time. Sudokus are an example of Latin squares. I bring this in because it talks about groups. A Latin square is just like a Sudoku, except I don't have the subgrids. So I have a sequence of n things, and I want to know that each row and each column has every symbol exactly once. And the only other example that shows up that we know of, or that we can easily use to generate these, are the Cayley tables of groups. You see in this one, this is the one that I had before, where I have Z mod 3, and the elements 0, 1, and 2 show up exactly once in each row and column. So morally, Latin squares are the Cayley tables of groups. They're not really that, because I have a multiplication, it has inverses, but I don't require any row to actually be in the standard order, which means I don't necessarily have an identity, and I don't require it to be associative. So this last one, this is my last slide. I even have a physical model of this. This is an example of how we can reverse engineer. So what we did was we took a puzzle and we built a group out of it. And the group described everything about the puzzle. One of the very, in fact, in some sense, most important ways that we understand groups in modern mathematics is by building models of them, either physically or, well, I'm using physically in a sort of hand-wavy conceptual sense. So space, not necessarily something you can actually get your hands on, or another algebraic form, it's simpler. And then we understand it via its action on this simpler thing. So the reverse engineer is build a puzzle starting from a fixed group. And this is an example of that. And it was done by Igor Krish, who's another algebraic topologist. He's at the University of Michigan. And Paul Siegel was an undergrad working with him trying to do this. And they found a number of puzzles, this is one of them, that use other groups. In this case, they're using small, simple groups. They're sort of the atomic building blocks for all finite groups, the ones that you can't decompose into smaller ones. And this one is on the Matthew group M12, and it has 95,040 elements. So the puzzle looks really complicated, and it is. It's very hard. But this number is also the same number of the ways you can choose 5 elements from a set of 12 where order matters. And so the Matthew group is exactly parameterizing the way you can take one set of 5 elements in a set of 12 to another set of 5 elements in the simplest way possible. So the way you can say it is the puzzle is what's called 5 transitive. If you can figure out how to move any 5 numbers to any other 5 numbers, then you know how to solve it. And it gives you a So here's some references. And the first one's a really interesting book. I recommend it. The second are sort of the papers that describe the counting